Start.
Okay. Good morning, students. In the last class, this is welcome to TRA Society webinar classes. And for this wave optics, second year physics classes, we are starting. In the wave optics, in the last class, we have discussed two main theories. One is Newton's corpuscular theory, and second one is Huygens wave theory. The main difference between these two, according to Newton's corpuscular theory, when light travels from rarer medium to denser medium, its velocity reduces. As according to Huygens wave theory, quite opposite. That is, when light travels from rarer medium to denser medium, its velocity decreases. There is a controversy between these two. This controversy is solved by Foucault's experiment by determining the exact velocity of light. Velocity of light in air, he calculated accurately 2.98 into 10 power 8 meter per second by his rotating mirror method. And next, he also find the velocity of light in different liquids, in water and oil. Like that, he has proved that by taking the velocity of light in different media, finally he proved that the velocity of light in denser media is less. This statement, this experimental proof supports the Huygens wave theory. So this is a death blow to this Newton's corpuscular theory. Totally, all are rejected his theory. From then, we are following Huygens wave theory. But the main difference, as we have already discussed in ray optics, light taken as a straight line, just we have taken lines. So as far as optical instruments are concerned, it is okay. But interference and diffraction, two more complicated phenomena of light are invented. The interference and diffraction could not explain with this ray optics and also Newton corpuscular theory, but these two can successfully explain by wave theory, Huygens wave theory. So what is this theory? We have already discussed in the last class also. That is, whenever a light source is considered as a point source, we have to spontaneously at a time, we have to consider the light as a plane, that is called primary wavelet. We have taken wavelets or wave front. What is a wave front? It is just like a locus point from the same phase, locus point of same phase from the source. So it is treated as a sphere, light sphere, you can imagine. That is called primary wavelet. This primary wavelet consists of number of points. You can imagine any number of points on this wavelet. Each and every point on this wavelet acts as source. Again, the source for secondary wavelet. These points are considered as the center, and we have to construct geometrically arcs with the radius of velocity of the wave in that particular medium and time. So by drawing all these, we can get another wavelet, which we call it as secondary wavelet. So like this, how these are secondary wavelet are formed, that also we have discussed. But you should remember, wave theory is related to three-dimensional movement of light, but a ray is just two-dimensional. That is the main difference we have to identify. That's why wave theory is somehow complicated than that ray optics. So you should understand three-dimensionally these waves. So all these waves generated from the source in the form of wavelets, secondary wavelets, move in forward direction. This is principle of Huygens wave theory. So based on this Huygens wave theory, how did he explain interference and diffraction, reflection, refraction, all we will see one by one. We have already discussed how he explained the refraction of wave. In the last class, we have discussed about refraction, and also finally we have derived Snell's equation also, Snell's law, n1 sin I is equal to n2 sin R. Now, this class starts with reflection of light. And today, if time allows, we can see remaining the important points in this wave theory, that is superimposition of waves, constructive and destructive interference. Interference phenomena takes place superimposition of two waves. If it is two-dimensional waves, easily we can explain. But as far as this wave theory is concerned, how did he explain? Let us see these topics for today class. Now let us start with reflection of wave. Yesterday we have discussed refraction. This is a reflection. So Mn is the plane of refraction. AB is the plane wave. We have to take that is incident wave front. AB is the incident wave front, is incident on Mn, a reflecting surface Mn. So this wave, while coming, it touches at A point first, as we have taken angle of incidence, this wave, incident wave on the Mn, that is the reflecting surface angle is I, that is angle of incident. Or to understand easily, we have taken at A and B two parallel lines. That line, just to make easy to understand what is incident angle, to see that a dotted line is drawn at point of incident A, that is normal. With this normal, the incident ray makes I. As in the ray optics are concerned, to understand the geometry of that, we are writing I. But actual I is angle BAN. AB is the incident wave front. So while touching this surface, what happens? While as it is a wave front, there is no possibility to, this is a reflecting surface, there should not enter into that. So what happens to A point? This A point returns, reflects in the direction of AE. So from this A is the source again. So we have to construct, according to wave theory, secondary wave front. How to construct secondary wave front? You have to take a circle, as A is the center. So we have to take an arc. How to take this radius? We have to draw an arc, means we should measure radius. What is that radius? Let us consider after t time, B reaches A point. After time t seconds, the point B in the incident wave front, at the beginning, at the end, we have taken 2 points, A and B. So B touches C. So the time taken to reach from B to C, the B point has to reach C, the time is velocity into time. BC distance we can get, velocity let it be V in the medium. So that V into time T, Vt is the BC length. So during this BC length, what happens to this A point? A moves forward AE in the direction, in the length of AE. So AE is exactly equal to the BC. Can you follow? Three-dimensionally, we have to understand this. AE is the radius of the arc which we have to draw to find out secondary wavelet. Where is that condition of this A point? A point moves back while touching this Mn surface at A, and A moves to this, and while drawing this arc, you join A and E points. AE is the, we call it as reflected wave. AE is the reflected wave. And if you draw a tangent to this E and join to C, EC, which we can get reflected wave front. AB is the incident wave front. After time t, what is the reflected wave front? EC. EC is the reflected wave front. Now, here we have to apply geometry. According to geometry, we have to understand. So, you know already I. Angle BAC is I. Where is R? R is angle ECA. How it is R? Let us say the normal, let us consider N. NAE. What is NAE? NAE is nothing but refracted ray and incident ray. So, both side by side to this normal. So, angle NAE is the refracted angle R. Okay. Now, what about the triangle? If you are consider AEC and ABC, there are two triangles, AEC and ABC. Comparing these two triangles and the angle at AEC, which we can take it as exactly 90 degrees at E, as this is the arc and AE is the radius. From the arc to radius line, always this line makes 90 degrees. So at angle A, 90 degrees. Now coming to the ABC triangle, where is 90 degrees? At B. That is angle ABC, it is 90 degrees. Two angles are equal. Okay. Now coming to the length, AE, what is the length of AE? AE length is exactly equal to VT, where V is velocity of wave in the medium, in the above medium. And similarly, what is BC? BC is also equal to VT, velocity into time. Therefore, in these two triangles, AE and BC are equal, which is equal to VT. And at angle E is equal to angle B. Or you can write angle AEC is equal to angle ABC. If it is NAE is R, what about ECA? That is also R. How it is? You can easily understand this, as this is in two triangles. Here clearly we are showing that, you see, MN is the reflecting surface, AB is the incident surface, angle BAC is I, BC is VT, AE is also VT, and one angle is 90 degrees. Considering these two triangles, that is AEC and BAC, are placed on the same base. Both these two triangles, you can see, on same base. So same base is AC. Both these two triangles are AC. AC is equal to AC, you can write. Therefore, these two triangles are congruent. So according to rules of congruence, when two sides are equal and also two angles are equal and one is the common base, in the congruent reactions, in the congruence law, we can tell angle BAC is equal to angle ECA, which we call it as angle ECA is R. So angle I is equal to angle R. So incident angle is equal to reflected angle. Therefore, incident angle, reflected angle, both are equal means it proved the reflection. So by using congruence of the triangles, we proved reflection. Only we are using geometry. You remember in the previous, refraction is also proved with the same geometry. So you draw the diagram carefully. That is most important. When this is given essay type questions or 4-mark questions, what is Huygens wave theory, and explain reflection with the help of Huygens wave theory. That is one question. And sometimes, what is Huygens wave theory, and explain refraction of light by using Huygens wave principle. So these are very important questions. What if you draw the diagram carefully while taking refraction and reflection, the diagram is most important. After that, we are going to see a smaller one, a short notes, that is Doppler effect. This Doppler effect you can see in sound. In previous classes we have studied when sound source and observer, sound source and observer are in motion, both these two are in relative motion, what happens? While the observer is at constant without moving anything, while this source of sound is moving towards him, just like a siren, a man whistling and coming towards you, then the frequency increases. At the same time, while the person is moving away from you, then it changes, the frequency reduces. Like this, when source and observer are in relative motion, you should remember what is the Doppler effect. When source and observer are in relative motion, the frequency of sound waves are changed. It seems to be increased or decreased. So this phenomena is called Doppler effect. So similarly, the same Doppler effect you can observe in light also. Here, what is moving away? Moving away. Here, this Doppler effect is, we can't easily identify in nature. Directly we cannot see. Why? Because the velocity, relative velocity is there in Doppler effect. The velocity of light is very, very high. During with high speed, we cannot identify. Very small fraction of this can be observed by astronauts. Astronauts can identify this Doppler effect at certain cases. So when the source moves away from the observer, here source means what is it? The stars. This is observed in galaxy. So stars are moving this side and that side. You are on Earth. So the distance between these two is very, very high. We will tell in light years or parsec. That is very big unit to measure a distance. So when the source move away from the observer, the frequency of light measured by the observer will be smaller. This is known as Doppler effect. So here, just like in sound, the frequency observed by the observer will be smaller when it is moving away. So this is how it is difficult to find out whether it is moving away or coming close to you. Means you are observing it and you should find whether it is changing frequency. Light is actually electromagnetic waves. Light is electromagnetic waves. It consists of number of wavelengths. So frequency and velocity is considered. Velocity is in vacuum 3 into 10 power 8 meter per second. Okay. Now the frequency, while we are talking about frequency, it is not easily find out. And also the wavelengths are from X-rays and electromagnetic waves. These wavelengths are very high to very low are existing. Gamma rays and X-rays, these are all electromagnetic waves. All these are light. All these are light waves. So where you can identify the frequency from where to where means, if you are on the Earth who should see the light means the visible light region only you can see. Is it not? We cannot see remaining X-rays or UV rays or gamma rays. All these we cannot see with your naked eye. Only VIBGR. We call the visible region is VIBGR, violet to red, violet, indigo, blue, green, yellow, orange, and red. These 7 colors we call it as VIBGR. In white light, these 7 colors you can identify with your naked eye. So in this VIBGR region, if there is any change, 0.4 micrometer to 0.7 micrometers of wavelength, the wavelength of this VIBGR is 0.4 micrometers to 0.7 micrometers, and less than 0.4 micrometers or higher than 0.7 micrometers, you cannot see. We cannot see our naked eye. So we can observe the change. Here, what is the Doppler effect? The change in frequency. Change in frequency we are observing means we can observe a color change between violet to red. Only if there is a color change in violet to red, then only there is a Doppler effect. We can see the Doppler effect for light only in VIBGR region we can see. And also only astronauts generally they can identify this. That's why we are taking a red shift. In this Doppler effect, what is a red shift? When a star goes away from the observer, why the star, generally the star is fixed. You are thinking it is fixed, but galaxy, total galaxy is in motion. Slowly they are changing, you know. So in the galaxy, number of stars are there. All these stars, total galaxy is moving. While it is moving, when a star goes away from the observer on the earth, we are on the earth, we are observing a star. It is moving away, then its light appears. Light appears to him with higher wavelength. So in the VIBGR, what is the higher wavelength? What is the lower wavelength? Red is maximum wavelength and violet is minimum wavelength. In between these two, violet to red, the remaining colors exist in VIBGR. So you should remember, when it is moving away, the wavelength increases. It seems to be increased. As a result, the wavelength in the middle of the visible region of spectrum VIBGR, that's why we are talking here about VIBGR, moves. When it is moving away, what happens? Wavelength increases. What is the higher wavelength in VIBGR? Red. Therefore, the spectrum moves towards the red end of the spectrum. It seems to be red. We can see stars are blinking with a different color. That is one of the reason for this. This is also mixed with the Doppler effect. So this is known as red shift. Red shift means wavelength increase towards red. Wavelength increases. Increased wavelength is red. Therefore, it is called red shift. Can you understand? When a star goes away from the observer, the light appears to be higher wavelength. Therefore, in the middle of the, even though the colors are blue, green, yellow, it seems to be red. The spectrum moves towards red. This is red shift. Similarly, there is blue shift. In the same manner, when a star moves towards the observer, opposite to this, if the star is coming towards you, towards Earth, you are observing it, then its light appears to him less wavelength, quite opposite to that. If it is moving away, higher wavelength, it is comes towards us, what happens? It looking lesser wavelength. As a result, the wavelength in the middle of the VIBGR region of spectrum moves towards violet or blue. Lesser wavelength means violet or indigo blue. relate to that, these three seems to be lesser wavelengths. Therefore, this is called blue shift. So, for the purpose of velocities of galaxies, we are giving some more details about this. The velocity is small compared to the speed of light. We can use the same formula which we are using in sound waves. We have already discussed. The fractional change in frequency, the change in frequency is very, very small. That is delta nu by actual frequency is equal to minus radial by c, where this minus radial is a component of source velocity, that E radial by V radial by C. Nu delta by nu is equal to minus V radial, that is V by C. V radial is component of source velocity along the line joining the observer and the source relative to the observer. Why it is, the velocity is also vector component. So whenever you join the star and you observer on the earth, you can get one line, and this velocity, in which direction the star will move. It is in galaxy. Star is in galaxy. So in galaxy, which direction it is moving means you have to take components of this vector, vertical component, horizontal component, we have to observe. So that velocity, in which direction exactly with respect to the observer joining the line. Whenever we are talking about vector, we should fix points. So one is observer point, another is star. The star is moving in different direction, whether it moves in the same direction of the line or above the line, perpendicular to this line, or some angle to this line. So whatever it may be, you can take V radial along this line. We have to consider the component. That component we have to take and divided by C. C means velocity of light in vacuum, that is 3 into 10 power 8 meter per second we have to write. So this V radial is considered positive when the source moves away from the observer. We have taken two cases. The star may move away or the star comes towards the observer. In these two cases, one is negative, another is positive. When you take this V radial positive, that we are talking, this moves away from the observer, you consider positive. If the star comes towards you, take negative. So by calculating this, we can observe how much change in delta nu, blue shift, red shift, which color actual, that is nu, and what is the change. If blue color is observed, for example, yellow color is observed as blue, means what is the nu of yellow, nu of blue? The change you find out, that is delta nu. By nu means actual yellow color, that is equal to, this is relative change in the fractional, relative change in the frequency is taken as minus V radial by C, where V radial is the component of the star velocity. Star moves towards you, you consider as negative, and moves away from the observer, you have to take positive. So this is the Doppler effect is very important in astronomy. While how the planets are moving, how to study of these movement of these planets and how these are, where is the position of the star, all these are calculated with smaller changes in frequency. They can find out velocity. While calculating velocity, they can tell the distance. Okay, all these we can easily calculate for measurements of velocity of distant galaxies, not only particular star, but distance. Some they are telling the galaxy is expanding. How they are telling expanding? Scientists tell it is expanding. The star is coming, a new star is originated. How these are telling? Means by study of this Doppler effect and this is very much useful in case of astronomy. So this is about, we are not going to details about this astronomy. You just remember the equation delta nu by nu is equal to minus V radial by C, where you have to take minus. It comes towards you, you should take minus V radial. It moves away from you, you should take positive. Just you remember this. And what is red shift and what is blue shift? Why? According to the relative motion of this star, star is moving away or moving towards you. In these two cases, you can observe red shift and blue shift. This is about short notes. You may ask me a number of times in the examination. Every time he is asking, and also in the NEET and examinations they will use this formula: delta nu by nu is equal to minus V radial by C. You should remember all these four. What are these terms? Delta nu, change of frequency; nu, actual frequency of the light produced by star. Similarly, V radial. V radial is component of velocity of the star. The velocity of star in different directions. That component along the direction, in which direction you have to take this component, along the direction of the line joining observer and star. Along that direction you have to take. That's why that component is V radial, and C is velocity of light. All these you have to remember. This formula is important. So this is about Doppler effect. What is the use of Doppler effect? The expansion of galaxies or velocity of the distant stars and galaxies are measured with the help of this. So this is today's important topic. And next one is, we are going to see coherent and incoherent waves. This is also very important as far as our lesson is considered. Here, coherent light waves, when you take two light waves, if the two light waves have same frequency and the phase difference between them does not change with time. Two light waves you have to take. These two waves, same frequency and phase difference. Phase means whenever we are using this word, you should remember angle. Phase means angle. The phase and the position of the particle, both these two interrelated. According to your previous knowledge in SHM, we have discussed a particle is revolving around a circular path. It makes 2 pi angle, 2 pi radians, that is 360 degrees. In terms of degrees, 2 pi radians means that angle is related to path. Both these two interrelated. For example, a particle is moving in the circular path started from A, and again it is reaching to this A point. How much angle it makes at the center of this circle? At the center of the circle, exactly, it makes 2 pi radians, 360 degrees. Similarly, for example, a particle is on the circumference of the circle, and exactly opposite to that position, the particle reaches. What is the angle subtended by the particle at the center? Can you understand my question? When the particle is moving on the circular path, instantaneously I have taken at a point P the particle on this circle, exactly opposite to the P point on the circle, the particle reached. Let us consider that is P dash. When the particle comes to P dash, what is the angle? Means exactly 180 degrees. It has to make at the center pi radians. If it is reaches to P point again, P to P point, it makes 2 pi radians, 360 degrees. Like this, the position, the distance of the particle from the center is identified by this angle also. So when waves are formed, the waves can be expressed in terms of frequency and also phase. So phase difference between these two waves should not change. Always the phase difference should be constant and also frequency constant. Both these two are constant, it is coherent waves. What are incoherent waves? Frequency is same. Both these two common point is coherent and incoherent. Frequency is same, but the phase difference between them changes with time. No order. Inorderly, they will rotate. Frequency may be equal, but the phase difference change. Second thing is when these waves add up and produce interference, that is the most important, which we are going to see in the next class. The interference and bright and dark fringes are formed on the screen due to these two waves adding up coherent waves. We can see bright and dark fringes. Hence, they can be seen by us as an orderly formed dark fringe and bright fringe alternatively formed. This is a pattern of bright and dark fringes formed on the screen. Whenever you observe a pattern of these bright and dark fringes, it is called due to interference of coherent waves. Here we are going to see nature of these waves. Those two are coherent. So coherent waves form a clear bright and dark fringes on the screen. But what about incoherent waves? The interference pattern, that what we are talking, bright and dark fringes produced by incoherent sources, does not remain constant. Even though the frequency is same, they are not following same phase. Inorderly they form. So bright and dark fringes width changes, the brightness changes, intensity and their bandwidth or the width of the dark and bright fringes changes. Therefore, only average effect can be observed on the screen. So what is this interference? How they are formed, these coherent waves? We will see in the next class. Okay, thank you all the students. Thank you for joining to my class. Okay, this is end of the lesson. Thank you.